Our final video dealing with titration focuses on the titration of a weak base with a strong acid. So we've done a strong acid, strong base titration. We've done a weak acid with a strong base titration, and now it's weak base with a strong acid. So let's go over a few pages. And you'll see here the titration curve for the titration of a weak base with a strong acid. Now notice that we're titrating a weak base. So for the first time, we're dealing with a higher pH at the beginning. So we're dealing with a base in our container. So we're going to have a pH up here, not up at 14, it's a weak base, but we're going to have a relatively high pH. And then as this titration occurs, we're going to get an endpoint, and notice that we've got an endpoint in this area. The same situation that happened with our weak acid strong base, we've got a shorter endpoint range. It's not as vertical, and it's lower. Look at where we're ending up here. We're ending up with our neutral or endpoint. I guess you can't call it neutral, but we're ending up with our endpoint being in the acidic range when we have that endpoint occur. So that's a weak base, strong acid situation. And then at the end, because it is a strong acid, we're going to end up with a curve that takes us down to a low pH because it is a strong acid. So equilibrium calculations have to be done for each one of these points. So let's just start out. Remember, we're going to do the same thing we did for the other two situations. We're going to show a calculation before we reach the endpoint. We're going to show a calculation at the endpoint, and then we're going to show a calculation after that endpoint. So the example here says we're going to calculate the pH when 100 milliliters of 0.050 molar NH3 is titrated with 10 milliliters of 0.1 molar HCl. The first thing you want to do, remember, in any kind of equilibrium problem is to determine what kinds of substances are involved. In this case, we've got a weak base and a strong acid. As soon as we've got one base and one acid in the system, we are dealing with titration. And since it is a weak base, this is going to, and with a strong acid, we can focus now on what we're going to have to do. We know we're going to have a strong reaction. The strong always leads the way, so we're going to have a strong reaction first. So we're going to start with CBAC, and then we're going to have a weak reaction. We're going to use rice at that point when we start analyzing our weak base. I don't know if I said acid or not, but it's a weak base. When we start analyzing our weak base. So let's start the problem. We know the strong drives it, and since this is strong, all we care about is the H plus out of the HCl. The NH3 doesn't split, so we end up with our strong part of the reaction being H plus reacting with the NH3, and it is strong, so we get that strong completion arrow, and we form NH4 plus. Remember, CBAC must be in moles, whereas rice must be in molarity. So we need moles first. As with the last video, I'm not going to do all those calculations. I'll do this first one and then I won't do any more. We've got 100 milliliters, so that's 0.100 liters times our 0.05 moles per liter for our NH3, which is going to give us a value of 0.005 moles of NH3. And then our 10 milliliters, which is 0.01 liters times our 0.1 moles per liter, gives us a value of 0.001 moles for our acid. So 0.001 moles of H plus. Now we are going to need to know in just a minute that when we start changing back to molarity, what our total liters are. So if we mixed 100 milliliters with our 10 milliliters over here, that's going to give us 110 milliliters that we're going to have total for this system. That's going to be important in just a moment. So we start out with this. We've got the completion reaction, which I wrote that C a little bit low. Our completion reaction up here. This is before. Then we're going to react all of the H plus because it's the one that's present in the least amount. So we're going to have that same amount taken away from NH3 and that same amount added to our NH4 plus. So after the reaction occurs, we're going to have 0 H plus left, 0.004 for our NH3, and 0.0010 for our moles of NH4 plus. Now we need to change that back to molarity. And we said we had 110 milliliters total, so we're going to divide both of those by, has to be in liters, 0.110 liters. And we end up with a value of 0.0364 molar NH3 and 0.00909 molar NH4 plus. So there's our molarities. Now the next thing we want to think about is what we have left in the solution. Do we have any of our weak base left? And yes, we do. So the weak part, the equilibrium part, is going to be focused on whatever's left in the system that's weak. And it's always going to focus on the weak acid or base if there's any present, and there is in this case. So now that we've done our change back to molarity, we can use these values to calculate our equilibrium system in Rice, using the Rice method. So NH3 plus H2O is going to yield NH4 plus OH minus. So there's our weak base reaction. And according to what we just calculated, NH3 is 0.0364 molar. We don't care about water because it's a pure liquid. NH4 plus is 0.00909 molar, and we don't have any hydroxide at this point. So our change is going to be minus X for NH3 and plus X for both NH4 plus and OH minus. So 0.0364 minus X, 0.00909 plus X, and X for our equilibrium values. So now we can set up our equilibrium expression. We know that Kb for NH3 is going to be NH4 plus times our OH minus over our NH3. Kb, it told us above, was 1.8 times 10 to the minus fifth. And that's going to be equal to 0.00909 plus X times X over 0.0364 minus X. And remember, we can neglect X, so that's going to be approximately equal to 0.00909X over 0.0364. So realizing that we just got rid of that term because we neglected X, we can solve for X by multiplying and dividing. I'm not going to go into that part of it. You can do that calculation. We end up with X being equal to 7.21 times 10 to the minus fifth molar. Now, molar what? We always want to check that, and it's molar hydroxide ion concentration, as you can see. So X is the hydroxide ion concentration. It wants the pH. We can't get that directly, but we can get the pOH as the negative log of this, which is going to give us a pOH of 4.14. pH, of course, is going to be 14 minus that value. So our pH is going to be 9.86, which is a value that we would expect given that we're starting out with a weak base and we haven't reached the endpoint yet. So let's go forward then and let's look at what happens when we do reach that endpoint. So we've got the same situation, the same reaction, strong reaction we talked about before. We're starting out with H plus NH3. The strong is reacting, is driving the reaction. We get that NH4 plus. It'll be the same reaction to start CBAC every time. If you do the calculations, we've still got the same amount of NH3 that we started with, which is 0.0050 moles. And now we've got, when we multiply that out, 0.0050 moles of H plus, and of course 0 of NH4 plus to begin with. Since they're both the same amount, we're going to subtract off both of them. I guess I didn't have to put moles again, and add that much to our on our NH4 as it reacts. So we end up, we've done the completion reaction, the before concentration, and now the after is this. Remember, we always change back to concentration, so we're going to divide this by total liters. We just did 100 milliliters plus 50 milliliters, so we've got 150 milliliters total, or 0.15 liters, which gives us a value for our concentration of 0.033 molar for NH4 plus. That's the only thing that's left in the system besides water. At NH4 plus, we can think of that as being an ion of the salt of that weak base, which means it's a weak base. What's water going to do? It's going to attack. There's no NH3 in this system, so we cannot start the reaction with NH3. We have to start the reaction with this NH4 plus. It's all we have left. So our rice, now that we've done the completion, our rice is going to start out with that NH4 plus being attacked by water. I'm so going to run out of room here, but I'm going to keep going, and if we have to go a little past, it'll be okay. So NH4 plus is being attacked by water. And when it does, we end up with water acting as the dirty, nasty hydrogen stealer this time. We are left with NH3 and then our hydronium ion, which remember we treat that just like the hydrogen ion. Our initial concentration, the only thing we have is our 0.033 molar NH4 plus. We don't care about water, 0 and 0 for these two. Our change is going to be minus x, and plus x. And we end up with our equilibrium concentrations being 0.033 minus x, and x. So I'm just going to pretend that this line isn't here right now. We'll put it back in a minute, but for right now, we'll pretend that that line is not there, and I'm going to continue on. So there's our equilibrium concentrations. We can set up our equilibrium expression now, and hopefully you will see that we have an issue because our equilibrium expression is going to be the equilibrium expression for NH4 plus. We do not have a K value for a salt ion, for one of those polyatomic ions. So this is the situation, remember, we faced the last time. When we have the endpoint, this is always going to be the situation where eventually we're going to have to find our new equilibrium constant. As soon as all we have left in there is that ion of a salt, that's what we're going to have to do. So our new K, and in this case it's going to be our NH4 plus is giving away a hydrogen to water, so it's acting like an acid. Our new Ka of NH4 plus is going to be, remember, 1 times 10 to the minus 14th divided by the Kb of its conjugate acid-base pair. And that is NH3, and it tells us up above that that value is 1.8 times 10 to the minus 5th. So when we divide that out, we get a new K value of 5.56 times 10 to the minus 10th. Now that we've got that value, we can set up our equilibrium expression for this reaction. We know that the Ka that we just found is going to be equal to NH3 times the H3O plus divided by the NH4 plus. And the new Ka we just found was 5.56 times 10 to the minus 10th. And that's going to be equal to x times x for the NH3 and the H3O plus, or x squared, divided by the NH4 plus concentration, which is 0.033 minus x. And remember, we can neglect x, which is going to leave this approximately equal to x squared over 0.033. Solving for x, we get a value of, I actually solve for x squared on this, so x squared is going to be 1.83 times 10 to the minus 11th. So square rooting that, we get an x value of 4.28 times 10 to the minus 6th. And let's remind ourselves what x is this time. X is H3O plus. That is our acid. So this is going to be, we are going to be able to find pH directly from this. So pH is going to be the negative log of that value, which gives us a pH value of 5.37. So at that endpoint, we do indeed have a lower pH value because of the action of the NH4 plus with water. So that's our pH. Now, hopefully you'll pause this and get that all written down, because I need to erase this because I need to do our final calculation. And our final calculation is for what happens after the endpoint. So we still have the same equation, H plus NH3, forming NH4 plus. This time when we do our calculation, still have the same amount of NH3. We've increased the H plus to 0.0060 moles, not concentration, the number of moles, remember. And the NH3 is still 0.0050 moles, and NH4 plus is 0 at the beginning. We're going to subtract off this time. We use up the NH3, and we're going to end up leaving some H plus behind. And we end up with 0.0010 moles of H plus. You have to keep track of that C back, or you're going to forget that last step. 0 NH3 and 0.0050 moles of NH4 plus. And here is where there's just no way to do it other than to memorize it. Now all we have left in the system is a very, very strong acid, the H plus over here, and a very, very weak acid, the NH4 plus. Remember, the strong H plus totally dominates the NH4 plus. The pH is going to come only from that H plus calculation, that H plus concentration that we're going to have. The strong H plus dominates the weak NH4 plus. pH comes from strong H plus concentration only. So let's find that concentration. We've now got 100 milliliters mixed with 60 milliliters. That's 160 milliliters or 0.16 liters. So we end up with our changed back to concentration value of 0.00625 molar H plus. We can get our pH directly from that. The pH is the negative log of that value, which gives us a final pH of this system of 2.20. And that concludes our discussion of titration for all three types of these systems.